So today I wanted to chat a little bit about some recent work I've been doing that sort of sits, I guess, yes, at the intersection of non-classical logic, model theory, and a little bit of category theory, to act as a proof strategy for some results that have otherwise been proving a little bit elusive. So the plan for how I want to actually talk through this a little bit is the detail on the slides is pretty minimal. So what I'll probably try and do is chat through things, and then when I want to detail stuff, I'll draw on here. So sorry, Lorenzo, you'll have to like whisper.
No worries,
It's okay up here.
Yeah.
I will say, and sort of broadly speaking, my hope for this is to more emphasize that I think this could be that I think this method is a potentially fruitful one in this context. Which I'll chat a little bit about why I have those kind of that intuition. Rather than necessarily getting too bogged down in the details, the downside of any kind of category theory stuff is a lot of it is a giant pile of definitions that don't really mean anything unless you're sort of living with them a little bit. But yeah, we'll sort of go through things and see how we go. So yeah, sort of the rough structure. I'll chat a bit about background, and then broadly how this work ends up is it kind of splits into three components. One is building up a framework that you need inside this kind of categorical world. There's a key statement which is called HP, and once you have the framework, that it gives you some meaning to it, but you have to actually put some work in to understand what its meaning is. And then, I mean, you actually want to check that it's the primary method for checking some kind of interested result. So then you want to actually establish it. And then I'll talk a little bit about the end of where I wanted to take this further. I sort of am describing this work at the moment as kind of like, okay, there's like some kind of like minimal viable version, which indicates that there's some reason to think that there's something to be said here, but actually like those sort of more interesting results are still to go. Yeah, are in the future, hopefully. Okay, so what's the starting point? The starting point for this is that over the last few years, there's been some work that's described various model comparison games through category theory. In particular, Samson Abramsky and Luca Recchio published a paper 2 years ago where they used that kind of framework to investigate preservation theorems at this kind of abstract categorical error. So in logic preservation theorems, they somehow link some syntactic class of formulas to semantic preservation. The classic example is the Warszawaski preservation theorem, which basically says that a formula phi is preserved under substructures, okay, structures where really what I mean by that is that if you have some model n and it's a substructure of M, and then M models phi, that implies that N models phi. And that holds if and only if the formula phi is equivalent with to some universal sentence. So, right, and by universal sentence, that's essentially something that takes the form for all, some number for all quantification, and then something that's quantified through. That's like the kind of that's the again like the sort of prototypical example of a preservation theorem. Actually, the one we're focused on today is going to be what's called the homomorphism preservation theorem. But I'll introduce that in a little moment. From the category side, the central idea is, or the central concept at the heart of all of this is gets what's called a resource index arboreal adjunction over a base category. And the point is that once you define this, you can state these purely categorical claims, which are with these HP, and then there's another one actually HP hash. And the idea is they capture concrete preservation theorems that we're interested in some particular setting when applied to a specific resource index arboreal adjunction. And then more than that, what Abramsky and Recchio did is they provided an axiomatic treatment where they said, okay, so here's how this framework works, and here in fact is a series of sufficient conditions for which HP and HP hash will hold for a given resource index arboreal adjunction. And so on the one hand, this lets you recover known results already, but then also lets you, this is why it provides a potential proof method for proving new ones. So the two main examples they have in their paper, one is the Ehrenfrucht-Freysse resource index arboreal adjunction. And this is over the category of relational structures. So we take a standard relational model, and then we think about homomorphisms between those, so functions that preserve atomic formulas. And in that case, what this HP actually means when you spell it out is it captures the homomorphism preservation theorem. So this is that so the HP. Okay, thanks. Sorry. So HPP, which is that phi is preserved under homomorphisms if there's any equivalent to it's called an existential positive sentence. Existential positive, where by existential positive, this is any sentence that's built out of the existential quantifier, the lattice conjunction, and the lattice disjunction. They also, the other main example they use is what gets referred to as the modal resource index of our prolongation. That's over the category of pointed cryptic key structures, and there it's this other statement, HP hash, that it holds, but then also it captures a very similar kind of preservation theorem, and this time that's for graded modal logic. So part of the motivation of doing this kind of categorical approach, because to one example you might think, well, this is going to end up being a lot of work for maybe not the largest amount of payoff. But there are a few good motivations for doing this. So the primary one, especially in the setting that they were already talking about, is that this proof method it avoids compactness. So it essentially provides a compactness-free proof strategy for these preservation theorems. So notably the homomorphism preservation theorem for classical logic, that's originally proved via compactness. And then in 2008, Benjamin Rossman published a paper where he proved it avoiding compactness, and then also, as a result, got a version of that theorem for finite models. So in general, this is an interesting approach in any setting where you don't have compactness. Classically, that's in finite cases. And then from our perspective, in the non-classical setting, there's plenty of non-classical modal logics where we don't have compactness. So this is a way of potentially getting something if you don't have compactness, given it avoids it entirely. Notably, if you have something that already fits into the categorical framework, then it might in fact inspire a preservation theorem you didn't even know you were looking for. So notably, if you do this work and you build something into a setting, what the appropriate notion of a homomorphism is and what the appropriate syntax fragment is going to be that you want to link it to may not be obvious, but actually now you could say, well, I have an abstract version of this. What does HP mean? If I can find out what that syntax fragment is and I can find out what the notion of morphism is, then great, I have a preservation theorem. Maybe that tells me something about the kinds of maps I should be interested in and the kinds of syntax I should be interested in. And then from a kind of slightly more meta level, one of the nice things that the category theory sometimes does is this does provide some kind of one precise way of understanding how different notions of equivalence and their preservation results are somehow aspects of the same phenomenon. So notably, the notion of equivalence in the modal case is really by simulation equivalence. And so what this setting does, at least in some sense, is tell you, okay, when we say things like Ehrenfort say back and forth systems are effectively by simulation systems in modal logics. This is one way of actually making that precise. They actually capture the same categorical phenomenon. Mostly our interest, or at least my interest thus far, has been on the first motivation of this. I'm using this or interested in using this as a compactness-free proof strategy for preservation theorems in the non-classical setting. So I should probably introduce non-classical model theory properly a little bit. So I tend to view the field basically from either two motivations. You can either kind of have a logical motivation or a more model theory motivation. On the logic side, the idea is we're providing semantics for first-order logics that are taking over some non-classical, usually many-valued propositional logic. So, Vukovic logic, Gödel logic, product logic that were referenced in the previous talk. What's the semantics for the predicate versions of these? Well, this is what one idea is we're providing the semantics for such predicate logics. On the other hand, you can kind of just view it from a straight semantics perspective, or from a straight model theory perspective, which is, for a model theory, we have these objects, classical models. They are things that are defined over the two-element Boolean algebra, and they say things are true or false. And we're just going to generalize away from that and now say that we're going to define over an arbitrary algebra as opposed to a two-element Boolean algebra. And again, to some extent, it's more that second motivation is more in line with my work. I tend to approach this from a kind of semantics first perspective, and later think about how it might actually explicitly link to certain predicate logic. Now, there is already some work on preservation results. Actually, I has done this previously. So there was Pilar and Amanda Vidal. They established a preservation theorem that linked. I just, rather than name them, I just linked up the connectors. So this was for models defined over a fixed finite MTL chain, and in this context we have strong conjunction because it's a fuzzy logic. So there, the syntax fragment is existential quantifier, both lattice connectives, and then strong conjunction. And they're linked to a notion of homomorphism for such models, and that was done by compactness. And then a few years ago, I proved a preservation result that linked the smaller syntax fragment where we drop the strong conjunctions. It's just kind of it's the same syntax fragment as the kind of classical one. That was then linked to what was I called at the time protomorphisms for models defined over UL chain. And that was proved basically by just taking such many the many value models, turning them into classical models, and applying the classical homomorphism preservation result to pull it back. Oh yeah. So both of these results have a little bit of a classical-esque flavor to them. To some extent, they somehow, to some extent, say that the classical parts of these models continue to behave classically. And that's kind of more obvious in the result I have, where it's like very obviously just kind of the classical connectives of the models. But even in the for the models over MTL chains, part of the reason you get the strong conjunction in that result is just that strong conjunction at a model level behaves exactly like lattice conjunction. And so it's kind of you get it for free. It's not really being used. And so again, actually, this sort of prompted some idea of, well, it would be interesting to look for preservation results that somehow really utilize the gradient notion of these models. Okay, so the plan to go through this, if you want to try this approach, if you want to try and apply the Abramskian regular approach to do something, as I said, it's kind of a three-step process. Well, when you have a concrete setting in mind, we need to build a resource indexed borrow reduction, if such one exists, for the setting that we're interested in. And once you've done that, okay, then HP says something, but you want to understand what it actually means. This actually turns out to be probably the hardest thing, or certainly the thing that causes the most issues. And then, given that they provided some sufficient conditions for HP holding, if you want to check whether HP holds, if you're hoping for it to be a proof strategy for a preservation result. And what hopefully become clear is that sort of current status of this is that this works in quite a general, well, this works in a relatively well-restricted, well-behaved restricted setting, which is models which will be defined over a fixed finite chain. I'm going to introduce these models explicitly in just a second, but yeah. Which is nice. That's kind of this like minimal version of this work that at least indicates that I think this approach like has meaning in the non-classical setting. And I have some understanding of the challenges that are going to come in generalizing the approach, which I'll talk about a little bit later. So that's the current status. Okay, so what's our base category? So the idea is we're just replacing as our objects are going to become these relational models over these non-classical models, so relational models over a fixed algebra A. What does that actually mean? Okay, yeah. So you take some algebra A and some signature L. I don't think any trouble. Okay. And then for a given predicate language, what is a model? Well, it's some non-empty domain. And then instead of interpreting relation symbols as subsets of the domain, they're now just functions from they're now just n-ary functions from the domain into the algebra. The second part of this is what are the arrows in the category? And in this case, we're interested in what are called, I'm calling monomorphisms. Not the best name, given that monomorphism has a meaning from category theory terms, but alas, I haven't come up with a better one yet. And so here the idea is we're asking that for all of these interpreted relations, whenever you take a tuple in your left model, the value after you basically compose with the function acting on the domain, it just can't get any worse, right? So it has to get this is this less than or equal requirement. Notably, this notion isn't, to my knowledge, particularly heavily paid attention to in the non-classical model, like the model theory, this non-classical model theory literature explicitly, but it comes up quite naturally in this work. It really is the kind of right notion of morphism to think about and apply these kind of results to, which is, I think, interesting just in its own right. Okay, so actually, from a category theory perspective, like viewing it as the objects of a category, that's all you need. You just need the, okay, fine, we have a domain and you have functions from the domain into an algebra, but they are intended to provide semantics of logic, and indeed we're going to need that later where we want to understand preservation theorem. So how do we define truth in the model? It's fairly natural. The idea is you have some truth value function. Again, this is going to go from sentences in the language into the algebra rather than just into like saying yes or no. At the atomic level, we just take it as the interpretation of the relation symbols. And then you close under all of the operations in the algebra. So, for example, right, like how do I define the truth value of phi and like phi lattice conjunction psi? Well, that's just going to be in fact phi, the value of phi taking psi, where you actually now take the whatever that connector was interpreted as inside the algebra, and you do that for every single algebraic connective. And then we need to understand how we're interpreting the quantifiers, and the idea here is they're infimum and supremum. So the universal quantifier is an infimum over all the values taken, and then the exponential quantifier is a supremum over all the values taken. Notably, if you stick A in as the two-element Boolean algebra and take the normal classical connectives, you have a classical model theory back. So there's some sanity here. Do I want to talk about that? I haven't. It's not on the slides, but something there's a slight quibble here that you might worry about is for certain algebras, these infimums and supremums might not be defined. So actually, as standard, we just make an extra definition that says, okay, these are what structures are defined as, and models are exactly those things which it in fact is always defined, so we don't have to worry about it. So so-called safe structures. And you just only ever deal with safe structures when you're interested in anything. But as it turns out, we'll see in a second, we're going to assume that the algebra is a complete lattice anyway, and so these are always defined, and for good reason. We have like good motivation to restrict to when A is a complete lattice. So here we don't have to worry about it quite so much. And well, this is the reason. So the first step is to establish some very basic properties of the category, and the first is that this category it's complete and co-complete exactly when A is a complete lattice. Like right to left direction of this, right? If you are a complete lattice, then you are complete and co-complete. It is relatively straightforward in the sense of the kind of thing you expect to be the limits is in fact the limits. But it's nice that in fact this goes in the reverse direction. So you're only complete and co-complete when A is a complete lattice, essentially because you can end up there are objects in the category that are going to witness the required infimums and supremums inside A. So if the category is complete and co-complete, then it will force A to be complete lattice. So in general, we're going to make this restriction. In the fuzzy setting, so when A is the unit interval, that's fine. That's not particularly alarming. It's maybe a bit more worrying if you're interested in like in non-linear algebras, but at least in a lot of contexts, this isn't a major restriction. So the first sort of like big category theory definition that I'm going to skim over a little bit is what's called a stable factorization system. So this is a pair of classes of morphisms for a category, where the main point is that any error in the category can be factored into these into a composition of maps from each class. There are then some additional conditions on top of that to sort of they behave nicely. The really easiest way of thinking about this, I think, is by example, which is that as noted here in which is that in set the surjective map, like surjective maps and injective maps are a stable factorization system. They're kind of the prototypical stable factorization system. That's that word. It's kind of the prototypical example, right? So if you take any functional map, then you can split it into its surjective part and then an injective. And in our setting, so for the category NP, it's essentially a raising of this is a stable factorization. So we take subjective monomorphisms on one side, and we take what are called strong embeddings. An embedding is just where an embedding being a map F, embedding, well, strong embedding is if and only if injective, which is the bit you expect from sets. And then we ask that the interpretation equals basically that you have a quality when you compose with the function. So, and so rather than just things not getting worse, then they're actually equal. And to some extent, you can kind of view this, right? The point is that F is injective, so it has some kind of reasonable notion of inverse, and that also is a monomorphism. That's really what you need to make a stable factorization system work, is that on the right-hand side, it has to be an invertible version of your morphisms class. Okay, from this point, we want to build up this resource indexed arboreal adjunction. So if we start with a category of a stable factorization system, for each object, we can define this set S of A, which is the set of embeddings. So this maps from our stable factorization system, which have that object as codomain. This is some kind of slightly refined notion of subobject of a category. And then a resource indexed arboreal category, so this is a special kind of category, is one with a stable factorization system where for each positive integer, there's some full subcategory that's closed under embeddings, and then for which a large, a significant number of properties of these subject objects have to hold. Yeah, it's like, I didn't think it was particularly informative to go through all of them in depth, but this is the key point is that it's somehow related to the behavior of embeddings of objects. That's what's necessary for this, and that's the key properties at play. And then a resource index arboreal adjunction is actually then just a family of adjunctions from some base category into this resource index arboreal category. Actually, I should check. Should I refresh the definition of an adjunction? Right, or are we happy?
Yes.
Okay. So an adjunction between category what do you see? What do you see on the left? And D on the right. We say two functors. So this is some kind of mapping from objects of C. Functor is a mapping that maps objects from one category to another and arrows from one category to another. And we say two functions form an adjunction, and where this has a direction. So F in this case is left adjoint to G. There's a couple of equivalent definitions. My usual standard one is the Homset definition. So what's the requirement? We ask that there's a bijection between the set of morphic arrows in the category. Oh, I'm definitely going to get this backwards. From the Homset of D, and that will be F. So this is for all objects X in C and Y in D. And we're going to ask that there's a bijection between the morphisms from F of X into Y, bijects with the arrows in the category C from X to G of Y. Okay, I think that's the right route. The idea here is that it's a weaker notion of kind of equivalence of category where between the images of objects of one functor and all objects you can map arrows of this kind exactly to arrows of this kind. They pop up all over the place in a sense that like sometimes it feels like there's always an adjunction of some kind floating around, and then the question is, what does it mean? So I guess to some extent I'm going to try and answer what it means in this case. So in some sense, a resource index arboreal adjunction is too complicated. It is actually just a family of adjunctions between some base category and this collection of categories. Well, so in our setting, how do we want to sort of construct this again? Well, we're going to start by giving all of our models an additional order, which is going to be a forest order. So we take all of our models, and we're just going to assume they now come equipped with some kind of ordering on the domain, and it's a forest order. So a forest order just being some kind of tree order, except you can have multiple routes. We technically need to expand on notion of morphism, but we just ask that it also preserves the forest order. And this is some new category, which we call RP. This isn't quite what we want. We want to focus it down slightly. So we introduce this condition E. What is this? This obviously well, we're going to look at objects, forest ordered models, where if two elements of the domain appear in some tuple that takes some non-zero value in the algebra. So in some sense, there's some level of true at some point for these two objects, and the model sees that because it actually witnesses it with some interpreted relation symbol. Then we're going to ask that they're comparable in the forest order. For anyone who's familiar with Geisling graphs, this is the natural translation of saying, okay, if you're related in a Geisling graph, then you have to be comparable in the forest order as well. This category is in fact resource indexed arboreal. You equip it with the same stable factorization system as our first category MP, but you just also require everything is a forest morphism as well, and that's still a stable factorization system. That's fine. And in this case, what are the special, like for each integer k, what's the special subcategory? It's quite naturally, it's the models whose forest order is at height at most k. So this is what's stratifying out the objects in the category. You're getting things that are somehow taller and taller and taller and taller according to their forest order. This is a little more transparent when we consider the function that we're going to construct. So for each integer k, how are we going to go from a base model to this kind of forest ordered model? Well, we're gonna move to the set of non-empty sequences of the domain of length at most k. Letting epsilon m be the function that just sends a sequence to its last element, because this is useful for defining something in a moment. These have a forest order, which is just the prefix order of sequences. That's a very natural forest order on the set of all non-empty sequences. So that's a forest ordered model, except we want to raise the interpretation of relation symbols. So how do we do this? Well, if you take the collection of sequences, we're going to say they're comparable exactly when each sequence in the collection is pairwise comparable in the prefix order. That actually really means that secretly there's just one long sequence that they all subsume under. Like just something really, when we say a collection of sequences is comparable, is if they are all prefixes of, basically you could order them out such they're all prefixes of the other with potential gaps. And in this case, then we can raise the interpretation relation symbol just by taking the value in the original model for the last element of each of those sequences. That's if they're so if they're comparable, we do this, and otherwise we just send it to bottom. So we just kind of get it's kind of like failing case. Like these are the bad sequences we just don't want to pay attention to. So we have to send them somewhere, and so we send it to the base value of the model of the algebra. This is in fact a functor. And it ends up being right adjoint to the forgetful functor, which just takes any forest ordered model and then just forgets about the forest order. So, and that's our injunction. And yeah, one has to go through and check that these things are in fact resource indexed and obey all the nice path all the nice sub-object properties, but it's fine. It's not too bad. Now, that's actually a slight lie. There's an annoying hiccup we have to deal with, which is the equality symbol. So we really do want to, we need to have the equality symbol interpreted in the language in order to make injection, in order for some functions to end up being injective that will need to be injective. The problem is we can't just put equality directly into the language and just assume we have equality all over the place, because in the raised category, in this resource index arboreal category of forest ordered models, that's too strong. So we compose with an additional adjunction which handles equality. So for any model in a standard predicate language, we can always just add in a new binary relation symbol that will be interpreted as equality. And in fact, in our context, crisp equality. So we don't just ask, we ask that it really does LIV equals the top element of the algebra when two elements are equal, and it equals the bottom element of the algebra when they're not equal. So that's what we mean by crisp equality. And then that functor is once again right to go into a functor. All you have to do is you take the quotient by the equivalence relation that this crisp equality induces on the domain, and then you just take the B redux to get the function in that direction. And then we actually look at this composite junction, and that's going to be our resource index arboreal junction. Where our base category is this MP that we started with, and now we have this kind of constructed forest ordered category. Okay, so that's the framework, but okay, now what I haven't even actually given you what HP is. The idea is we're going to try and extract a preservation theorem out of this. So we'll state it categorically, and then I'll try and give some meaning to it. So given a resource indexed or borrowed junction between C and E, what would be in category C and E, an object, we can basically use this adjunction. The idea is we can use this to define relations on objects in the base category by their behavior in the resource index or borrow category, so in the cover. The most straightforward one, I don't really have a way of saying this in words easily, so I'm going to say, like, I don't know, A maps CK to B. So these are objects in the base category. We're going to say that they have this relation of mapping CK. Exactly when there's just any morphism between the image of between their images in the through the adjunction. That one's relatively straightforward. There's a sort of dualized version of it, but it's a bit more complicated. So this version, this like left-right arrow CK relation, that's defined as their images being what's called bisimilar. Again, what being bisimilar means in this category setting is like a two-page definition by itself. So it didn't feel particularly helpful to sort of laboriously go through it. It will probably have slightly more meaning when we actually give it the concrete meaning we have, but annoying, so it's a bit frustrating, but there we go. Given any kind of relations on subcategories within a category, just to introduce some terminology, we're going to say that a subcategory is closed under a relation, basically when if something belongs to the subcategory and then that object relates to another, then that thing is also in it. That's very standard. And then we use saturated to just mean the kind of the dual version of that. So when R is an equivalence relation, and then this property holds, then we say that D is saturated. And what HP does, what HP actually says in a categorical setting, it says, okay, if you have some resource index or borrowed adjunction, then for any full subcategory of our base category E that's saturated under this left-right CK relation, so when the images or objects bisimilar implies that your category map has to match. In that case, then D is closed under the morphisms of the base category exactly when it's closed under this arrow CK relation. So that's the like categorical statement of HP. That's all well and good, but we now need to understand, well, okay, what does it mean in the context I'm actually interested in? So the kind of first part and the like real category theory, model theory part of it is basically confirming that these categorical relations that we just introduced in this particular setting mean some kind of variant of a back and forth system. So in this case, this is where perhaps this left arrow one is a bit easier. So in the specific case that we're working in this resource index or borrowed adjunction we've constructed, you have this dual left-right arrow relation between two models, exactly when there's a back and forth system between those two models. So, and a back and forth system here, it is the familiar one from classical model theory. All I mean is just a system of morphisms for which the back and forth property holds. That is, for every element, if you take a partial, if you take one of the maps in the system and you add in, you consider some new element of the domain, then there's some corresponding element in the target domain that you can extend to, and vice versa. And we ask that they are partial isomorphisms, which just means that they are bijective on the restricted domain that they act on, and they maintain equality of all atomic relations. So that's a back and forth system in this context. The one-way version of this relation, that corresponds to what's called a fourth monomorphism system. So this is exactly the same kind of thing. It's a system of morphisms. Now we only require that you can extend from M to N. So if you have some map in the system, and I give you a new element of M, then there must be a corresponding element of N such that I can extend, but I don't require the reverse. There's no back. And rather than being isomorphisms, they need only be monomorphisms. So they're just partial types. And this is really what all of that kind of categorical work is encoding. It's a way of encoding the existence of these kind of systems of maps into a categorical relation. Now, in classical logic, this is actually essentially the same thing. But then you're done, because Ehrenfeld-Frisé works nicely. This is all kind of the stuff you'll see in early model theory classes, that, okay, if you have back and forth systems between classical models, then they're elementarily equivalent exactly then, and so on. Unfortunately, in the non-classical setting, in these many-valued models, the relationship between the existence of such systems and preservation results and elementary equivalence is a kind of substantive topic in its own right that's hard. So this is where this kind of first major restriction of the work comes in, because for now I'm just going to say, okay, let's restrict to the setting where this does work, so I don't have to worry about it so much, and I get something out concrete. And in this case, that is for for when the algebra is a finite chain. So in that context, you have a back and forth system exactly when two models are strongly equivalent. So the formulas with quantifier rank at most k take exactly the same value in the two models. That's point 2 in the lemma. For understanding what a fourth monomorphism system does, this is where we actually finally we get a notion of what our syntax class is going to be. So here we're going to start talking about existential positive formulas. These are formulas in which, okay, I'm going to say all atomic formula occur positively. What do I really mean by this? Essentially what I mean by this is that if you think of, if we think of a formula with some number of atomics as a function which takes interpreted atomics, say like a PM sentence, as like R1 and R1, and fine. Right, like we can think of any formula in our language somehow as a function that takes this argument and outputs some value of the algebra. When I say positive, I mean that each atomic, each atomic formula occurring in the formula, if then you have that let's say, well, this is like the interpretation of phi in the model. If I were to increase the value of this atomic formula, so if I had been the phi rm do was less than or equal to, I don't know, some key m, then that would imply that I am this original thing. Oh, I shouldn't have put something there. Also increases. Right. So in again, like this kind of exactly captures at least some of the ideal behavior of positive sentences in the classical setting. So this for any sentence that's built classically, for any sentence that's built out of the existential quantifier and either of your lattice connectives, this exactly occurs. If you ever increase the value of an atomic formula, if you make something that was previously false true, then the sentence can only ever go from false to true. This really is just the kind of language agnostic description of this. So any algebraic connective which is monotone, right? So it has the property that exactly this, that if you increase in the algebra, if you increase the value, then it also has to increase. You can include any of those, but it also allows you to do things like include algebraic connectives where that may not be the case, but multiple iterations do. So the usual example of this would be implication. So implication in its left argument is monotone, right? If you take something like they could potentially reduce in true value if you increase the true value of the antecedent, right? If an antecedent goes from false to true, your implication could go from true to false. But if you have double implication, so you have an implication nested inside twice, then that's now it's once again a positive occurrence. An atomic occurring inside the antecedent of two implications has become positive again, and so this is the syntax class that we're accounting for now. So just to introduce some notation to it, it's easier. We're going to write that sort of n maps existentially positively to n to just mean that for all existential positive sentences, if they take the value 1 in the original model, then they're going to take the value n in the target model. This greater than or equal to 1 is reflecting this kind of standard notion of modeling in the fuzzy case, where this is the most transparent, but it's not super. We're not super sensitive to the greater than or equal to 1, but that's what we're going to use here, just because it's what's kind of used most of the time. So Yeah, so as I said, in this setting, in the nice setting where your underlying algebra that you're defining models over is a finite chain, then these systems of maps match nicely with the syntax preservation relations, just as they do classically. This isn't quite enough either, because the idea here originally was we want to talk about when a formula is preserved under certain types of maps, when it has a specific equivalent, so like an actual syntax piece that it's equivalent to. So you then need an additional result that links those preservation results of syntax to specific formula. The first of these is actually straightforward. If you look at the models of the formula, then that is in fact saturated under strong equivalence, or equivalence classically, so which is finally fairly obvious. And then it takes a little bit more work to prove that if you take some subcategory of your class of models NP, then it's upward closure with respect to this existential positive closure, exactly when there's actually a witness for this. So there is in fact some existential positive formula, and it's exactly that subcategory is exactly the class of models for that. This also relies. This only works in certain settings, this only works in certain settings as it stands. But okay, in this nice restricted setting, if you link all this together, we actually do now have a concrete meaning of HP. So we get a preservation result, and what does it actually become? Okay, when A is a finite chain, if HP holds for this resource index or adjunction, then all sentences of quantifier rank at most K, they are preserved under monomorphisms exactly when they are logically equivalent to an existential positive sentence. So the syntax class is slightly generalized. It's now anything where atomics can occur positively, and then our map group, like the maps that we're preserving under, is now this group of monomorphisms. So we've somehow managed to really capture the notion of gradedness in these models, at least somewhat, by linking to monomorphisms. Okay, now that's actually, okay, that's what HP says, but now we want to check if it's true, right? The idea was to try and get this as an actual preservation result. So this goes back to Ramsky and Radio's own work, where they gave these sufficient conditions. They gave an axiomatic account. I'm going to flash these up. Again, the details don't massively, I don't think the extra specific details aren't the thing that's mostly interesting here. It really is just that there are, in fact, these are the sufficient conditions, so they give it a relatively short list. And now we've reduced the scale of checking this preservation theorem, or we'll get it, provided we can just check these rather than having to prove it directly. The first two, E1 and E2, they are properties of the underlying base category. Whereas the four claims A1 through A4, they are actually about the behavior of the adjunction, the family of adjunctions. And as it turns out, when A is finite, so it doesn't have to be a chain anymore, but at least when A is finite, all those preceding axioms hold for this resource index borrowed adjunction. And so great, that gives you some kind of result. If A is a finite chain, then in fact HP does hold, and we now know what that means. We get this sort of monomorphism preservation theory. So, okay, that's the, as I said, this is the kind of minimal version of this that says that, in fact, non-classically, these models can be fitted into these contexts. You get the similar kind of results. Yes, there's some problems, but it's a sort of intelligent, or what's the word I'm looking for? Yeah, it's a plausible system to investigate, and a method of proving some kind of preservation result that maybe wasn't particularly natural to go looking for initially. But the real hope would be to expand from that kind of nice restricted setting and try and understand if we could get this for other settings. So there's kind of two different forks here. One is just applying to settings where we have to change something in the construction. So one of the cases I'm interested in is looking for models where your algebra A is an ordered semi-ring. In that context, you have a very different notion of games that are interesting, that they've already been studied in the literature, but because they're different, you need to alter the construction. So the resource index borrowed adjunction we've constructed wouldn't be appropriate, but it seems plausible that some other altered version of it would be, and then you would already know what HP means, and you get that preservation term in that setting, but you need to alter the construction. And then I'm always interested in trying to understand for the situation where models are defined over varying algebra. So thus far, we've been looking at the category where your models, you take as fixed algebra A and you just define models over that, always over the same algebra. That's quite naturally semantically, because it's a bit simpler, but logically, you really want to allow your algebras to vary amongst the variety that represents your non-classical logic. So we want to understand, okay, how might we have to adjust our basic notions? And again, these kind of the underlying adjunction if we allow the algebra to vary. More substantially is, okay, can we actually handle potentially infinite algebras? This would really be the most interesting thing, especially in the fuzzy setting, because we were interested in the unit integral. So there's some suggestion this is going to be plausible if the variety generated by A is locally finite. In that case, some of those questions around what HP means still work, so that's reasonable. So, okay, that's still a relatively harsh restriction, but it's at least a little bit more general than actually a specifically finite A. The problem, though, or at least another significant problem, is that this A1 and A2, so to go back, so these two statements here, they very clearly and obviously fail as soon as A is infinite. It's very easy to get those to fail. And so we don't just get that, well, the sufficient conditions around skin regular given are enough. We would have to actually go in and ask, are there weakened notions of those two results that do hold when, say, the variety of A is locally finite, but still is enough to actually get HP. And that requires really getting into the weeds of how HP is recovered from these statements. So there's some intuition that it's plausible, especially in the case of A1, but weakening A2 looks a lot harder. And so that's a potential sticking point for pushing this beyond finite algebras. So yes, that was everything I want to talk about.